Let's kick off this explainer with a look at our title. Why did pterosaurs have head crests? A prehistoric mystery. Welcome, everyone. Today we're investigating one of the absolute most bizarre prehistoric mysteries in the entire fossil record. We're talking about pterosaurs. You know, those undeniable kings of the Mesozoic skyline. We're diving into exactly why these giant flying reptiles evolved massive, seemingly completely impractical headpieces. Let's start by looking at our first real suspect. This is a creature named Thalassodromeus sethi. Picture this. 100 million years ago, in what is now Brazil, this pterosaur is stalking small lizards in the undergrowth. Its species name, Sethi, actually comes from the Egyptian god Seth, because its wildly irregular head crest looked just like the god's side profile. Now, really think about the sheer scale of the proportions here. This animal's head was almost the exact same size as its entire body. I mean, if it were standing right next to you, it'd be a little shorter than the average human. Yet from the tip of its spear-like beak to the very back of its massive head crest, that measured almost 1.5 meters long. So why would a flying reptile evolve a giant, heavy head? This brings us to a glaring biological contradiction we really need to address. We all know the golden rule of flight, right? You've got to be lightweight, streamlined, and perfectly balanced. So how on earth could an animal with a 1.5-meter headpiece strapped to its skull actually be an efficient flyer? Honestly, it sounds like an aerodynamic nightmare. To understand how this happened, we've got to trace the family tree. Let's map out the timeline for these sky kings. 220 million years ago, in the late Triassic, we have the rhamphorhynchoids. Then in the late Jurassic, pterodactyloids appear. And finally, by the mid-Cretaceous, giant crested pterodactyloids totally take over the skies. Basically, if we rewind to the late Triassic, pterosaurs were not the giant, agile beasts we usually picture. The early gliders eventually step aside, and this completely new, giant, crested group moves in to dominate the air. So comparing the two groups, the original group, the rhamphorhynchoids, were small, about eagle-sized, with teeth, long tails, and they were mostly crustless, with just a few tiny crested exceptions. Versus the pterodactyloids, which were larger, vastly better flyers, had lightweight beaks, short tails, and massive, wildly diverse crests. The new guys arrived and traded heavy teeth for lightweight beaks. Their wings got thinner and longer, making them way superior in the air. But here's the paradox, right? As they became better flyers, they sprouted this explosion of giant head crests. Why would the most advanced flyers evolve something that seems like it would literally just get in the way? That brings us to hypothesis 1. Built for flight? Were these giant structures actually built to help them navigate the skies? Okay, back in the 1940s, researchers threw out a rather, out there idea, the giant rudder theory. They assumed these crests physically helped steer the animal through the air. But when we actually break down the mechanics, the math simply doesn't add up. First major flaw, the directional force provided by a head crest is absolutely tiny compared to just a slight adjustment of their massive wings. And second, think about it practically for a second. Steering by turning your head means you literally can't look where you're going. You'd be totally blind to obstacles right in front of you. So yeah, the rudder theory, we can toss that out. But hey, that doesn't mean there weren't some small aerodynamic advantages for specific species. Take a look at the Nyctosaurus's aerodynamic advantages. 1. Its antler-like crest supports a large membrane. 2. This membrane acts like a yacht sail. And 3. This reduces energy consumption over long-distance sea flights across ancient seaways. Nyctosaurus was this golden eagle-sized pterosaur that lived around 70 to 80 million years ago. Researchers strongly suspect that unusual crest basically turned its head into a sail. It lived in what is now Kansas, which, back then, was this ancient seaway cutting right through North America. A 2009 study found that having a head sail would save precious energy during those long oceanic cruises, which perfectly compensated for its smaller wings. Then, of course, there is the famous Pteranodon and its beak counterbalance theory. People thought its iconic backward-sweeping crest acted as a counterbalance for its massive beak, reducing the muscle strain needed to keep its head stable. And sure enough, wind tunnel studies showed this could help a tiny bit. But here's the major flaw. Crest size and shape across the species varied wildly. Some individuals had crests that pointed straight up rather than backward. I mean, if anything, an upward-pointing crest would make physical balance even harder, not easier. So here is the million-dollar question. If it wasn't just for flight, then what? If aerodynamics and flight mechanics were not the primary evolutionary drivers for these massive structures across the board, what was really going on here? Why spend so much precious biological energy growing them in the first place? Well, that leads us directly into hypothesis 2, dressed to impress. We are talking about sexual selection. Let's look at the pterosaur dimorphism evidence. For Darwinopterus, males had an elaborate crest, while females had no crest. And we know this for sure because one was actually found fossilized with an egg. For Pteranodon, males had a large crest, and females had a tiny crest. This is the smoking gun, folks. When we look at large sample sizes, a clear pattern of sexual dimorphism emerges, meaning the males and females looked drastically different. That Darwinopterus fossil proved beyond a shadow of a doubt that the completely crestless skull belonged to a female. So this basically proves the primary function of these skulls was visual display. The crests got bigger over generations simply because females preferred to mate with the most impressively crested males.
But some pterosaur species show absolutely no difference in crest size between males and females. How does sexual selection explain that? Well, we just look at modern birds. For example, European starlings. Both sexes select mates based on iridescent throats. Versus puffins, where both sexes have colorful beaks, mate for life, and share parental care. Because both puffin parents are investing heavily in raising the young, there's a strong selective pressure for both sides to be highly choosy about their partner. It is entirely possible that some pterosaur species had a very similar dynamic of mutual ornamentation and shared parenting.
What you really have to remember here is what we can call the peacock principle. Passing on genes is the ultimate evolutionary goal. Massive plumage is a severe physical hindrance to survival, but dazzling displays win mates despite making flight and hunting much harder. In the game of evolution, passing on your genes override to almost everything else. A peacock's massive tail makes it a huge target for predators and a worse flyer, but they evolve them anyway because a dazzling display wins mates. For a pterosaur, a giant head crest might have made daily survival and flight a total pain, but if it was the only way to secure a mate, evolution pushed forward with it anyway. But here is the plot twist. Hypothesis 3, evolution's multitool. Check out this comparison. The large surface area is later utilized for vital heat regulation. What's truly fascinating is how evolution just loves to recycle its own biological inventions. Rabbits and elephants originally grew those big ears to hear better. But over time, because those large flat surfaces were already sitting right there, the animals secondarily adapted them for a completely different yet vital function, cooling down. Evolution rarely lets a good structure go to waste. And that brings us right back to Thalassodromeus. Its massive head crest was irrigated by numerous blood vessels, likely serving a secondary function for heat regulation. Remember our lizard-stalking friend from the beginning with the 1.5-meter head? When researchers actually studied its crest, they found it was heavily irrigated by a vast network of blood vessels, functioning remarkably similar to a rabbit's ear. So while these enormous structures almost certainly evolved initially as a flashy display to attract mates, once they were there, they doubled as an ancient biological air conditioner. It literally helped the animal regulate its body temperature under the sweltering Mesozoic sun. Talk about a win-win. So, with so many fragile crests lost to time, what other mysterious purposes did they serve that we have yet to discover? As dominant as pterosaurs were, they're actually pretty rare in the fossil record. Their bones were hollow, super thin, and fragile, especially these delicate crests, meaning they just didn't preserve well over millions of years. We are literally piecing together this massive puzzle from tiny fragments. It really makes you wonder, right? With so much physical evidence completely lost to time, what other incredible secrets and bizarre adaptations are these prehistoric sky kings still hiding? I'll let you ponder that. Thanks for joining me on this explainer, and keep questioning the incredible history of life on our planet.